start with the Bellman equation. So the key observation that you might, we already have seen, we talked about this before, is the kind of recursive property you see in the future return. So what is the point here? Say that I want to just compute the future reward at one particular time t. So when I am at time t, I do one action, I start getting reward, right? So I get my next reward. That reward is RT plus 1, right? So when I equal by 0. And then after that, I change my state, I do another action, and then again I get a new reward. That is RT plus 2. And then the distribution of RT plus 2 is again described using my policy and the MDP, right? And you keep on going like this. Now the thing that I can do, I can just start expanding this summation, so I can start writing it down in this form, and I have the immediate reward plus discount factor times the next reward, and so on towards the end. And now I can just factorize any term but the first term. So I can just look at I keep the first term, and then I take discount factor as a factor out of the expression, and then I'm going to remain with this expression, right? And this expression that you see is again the future reward when you just go one state further in time, right? So it means that looking at RT plus 2, this is the immediate reward that you get when you are in your next state, right? So when you are in state ST plus 1, say that you already have passed this state, right? You have done your action. After doing your action, you get your reward. You change the state, right? In that state, once you do your next action, you're going to get the immediate reward, which is RT plus 2, right? And then after that, you again get RT plus 3, and so on towards the end, right? Everybody's clear? So this guy that you see here in the brackets is the future reward that you get in the next time step, right? Not in this time step. So you can eventually write it down in this form. So I can say that whatever is my future reward is my immediate reward plus discount factor times next future reward, right? Everybody agrees? So this means that like I'm right now at this particular state, I do an action, I see one immediate reward, right? If I do know what I'm going to get after that, then it's over, right? Because I can take that future reward, add it up to my immediate reward. This is actually the future reward at state ST at the particular time t, right? Everybody's clear? Questions? Everybody sees what I'm doing? Right? So this is a kind of recursive property because it is telling you like the next time reward is somehow related to your current time future reward, right? Future return, sorry. Right? And then we can use this fact to develop one fixed point equation, which is going to make the evaluation of the value function much easier for us. So how we can do it? Let's say that we are playing with the particular policy pi. If I want to just compute the value, what should I do? I should look at the reward return, the future return, and I take the expectation with respect to policy pi, right? So this means that this is the definition of the value function. So say I'm in the particular state S, right? This is the state that I am in at the particular time st, right? At particular time t, I'm in the state S, right? And then I am in this state. I want to see if I play with policy pi, what's going to happen in the future. So I'm going to just write down the future return, and I take the expectation, right? Now, next thing that I'm going to do, I'm going to replace this future return with the expression we found in the other, in the previous slide, right? So the future return, gt, is going to be my immediate reward, which is RT plus 1. This is the reward that I get immediately after playing my policy. And then I add up the future reward of the next time interval. That is going to be the future return of this time interval, right? OK. Now I can expand this expectation, right? So I can open it up. I can write it down expectation of the blue term plus expectation of the yellow term, right? Everybody's cool, right? No magic, nothing happened yet, right? Now, this first term, what is this guy? Do you remember this? expected immediate reward, right? With respect to policy pi, we computed it once before. If you want, we can compute it once again, but I guess you don't want it, right? So, but it was quite easy, right? Because you are in this particular state S, you would say, I do know what is the probability of the next state. I do know what is the probability of the immediate reward that I get. I just average with respect to that, right? If you remember. Okay, so this guy is the immediate reward that we showed it, but what about this other term? Do you know what is that? Any guess? Any suggestion? So I am computing the expected future reward given that I am in state S. Isn't that the value function at state S? Yes or no? Yes, yes or no? Who says yes? Who says no? Great, so we have a couple of people saying no. It's not. It's not the value function when you are in state S. Why? Pay attention. This is a very typical mistake. To be honest, I did the first time I was studying reinforcement learning, okay? No worries, that's totally normal. Because you see, you would say, okay, future reward when I am in state S. But what is this state S? This state S is happening at time t, right? So you will assume that your state at time t is S, but you're not talking about your future reward at time t, you're talking about your future reward at time t plus 1, right? So you're skipping one time step, right? If you want to write down the value function at a state S is the future reward of that time given that you are in state S, right? So you see the difference. There is one time step that you're skipping, right? So you're in this state. You're not saying what is my expected future reward. You say that I skip one time step, then I want to see what is the future return, right? So there is one step difference. And so you cannot say that this guy is exactly as this one. So this expression, this one which I kept as a question mark, is not the value function at state S. Everybody's clear? Questions? Yes?
Can you explain again the logic behind the difference between g sub t and g sub t plus 1? Logically speaking, how they're different.
GT and GT plus 1? This is like, say your game is going to, like your trajectory is going to terminate at some point, right? Now, GT is the reward that I get, say t equals by 2, okay? GT is eventually the reward that you're going to get at time 3, 4, 5, so on till the last time, right? But GT plus 1 is the reward that you are going to collect at time 4, 5, 6, and so on, right? So there is one time step difference, right? Now, if you were in time 3, then it was okay. Like if instead of ST here, instead of ST, I have ST plus 1, then it's okay. This is the value function at point S, right? Because I am giving this state at the particular time, and I'm talking about the future return, right? But here is not the case. I am talking about this particular time step, but I'm talking about the future return, not immediately after, but by skipping one time step, right? So that is different, right? Cool. Questions? No question? Okay. So if you got no question, now the thing that I want to do, I want to see what can I do with this expression. And as you might guess, I am going to again use chain rule, right? We have done it all the time in the previous lecture. We should do it again, right? But I promise it's not going to be as messy as last time. Okay? So look at it here. So we have this guy. So I want to know what is the expected GT plus 1, given that I am in this particular state S right now. And I want to expand it. Okay? What do you suggest that I add here, first of all? what should I add here to somehow get this guy something known? Yes? Action? Why action? If I know action, then still the time step is a skipping one, right? Next state, right? If I know the next state, then I know the next state. I'm talking about the return after, right? It's again the value function, correct? Everybody agrees? So I'm going to put this guy here, which is the next state, right? So I would say next state is one particular state, Sn. Okay? Then things are now making sense, right? So this guy, you might be able to compute it because you are just going one step forward in time, and now you're talking about the future return, right? You are at the same time as you are talking about the return, that's fine. Now, that aside, right now don't think how you want to compute it. I just add this red term here. What should I do to relate this guy to this guy? Multiply with the probability of the next state and then sum it up over all possible cases, right? So I should do the marginalization. Everybody agrees? Everybody's cool? So I would say the probability that I get from state t, s, to a state Sn in the next time step, I multiply it to the corresponding expectation, and then I sum it up over all possible states, right? So I am in one particular green state. I would say that the chance to go to the other state is this, the other state is that, and so on. Now, I assume that I have gone to another state. I compute the return, expected return, right? And then again for another state, expected return, and so on. And then I average everything up, right? Cool? Everybody's clear? Questions? Great. So if that is clear, then let me write it down in this form. So I'm just presenting everything compactly. So the green guy is the state that we are right now in. The red guy is the next state in time. And then I just drop that S and ST. Sorry, ST and ST plus 1. And just keep these here. But the colors should make it clear, right? OK. Now, I want to compute this one. This means that I need to know the first term and the second term, right? Now, for the first term, anyone knows what is the first term? What is this expectation of the return in time t plus 1, future return in time t plus 1, given that in time t I'm in state S, in time st plus 1, I am in state Sn. Anyone has a clue? Yes? Any idea? Yes? That's going to be the value function at which point? State Sn. Great. Yeah. So this guy is a value function. This one, any idea how I can compute the second guy?
From the transition model, but you have to sum it over all the actions.
Great. Transition model, and you need to average it, sum it up over actions, right? And the actions, again, you can describe it by your policy, right? Their distribution. So we can compute these two guys. So let's compute these two guys. For the first guy, I am at time t in state S. I do some action. You don't care. I just jump to the next time step. In the next time step, I'm going to get to state Sn. And then I do some action, and I keep on going, right? And I want to just find out what is the expected future return, right? And if you want to just compute that one, the key point here is that you don't care anymore about previous time, right? Because in the previous, this is a Markov chain, right? An MDP is just explained with the last guy in the chain, right? So what I can say the expectation of the future return is going, given that the state at time t is S, the state at time t plus 1 is Sn, is eventually this term, right? So I can get rid of the time t. I already know time t plus 1, right? You know time t plus 1, no need to chain. Everybody's clear? Everybody agrees on that? Yeah? And now this other term, this right-hand side that you see, this guy is again value function. Only difference is that it's computed at the particular point Sn, right? Cool? So this guy is the value function at Sn, right? Given that you are playing with your policy. Questions? No question? Yes?
Quick clarification. So the value function is also time independent, right? Because it only
You
depends
assume
on,
it's time independent, exactly.
So it only depends on the state, not the time step.
Yes, state, environment.
Yeah.
Environment and your policy, right? Right. That's correct. Questions? No question? Okay. So that guy is known. The other thing that we wanted to know is the distribution of the next state given our current state. Well, you can always do it by doing marginalization, right? If I do know the distribution of Sn and the action given state, then when I sum it up over all the possible actions, then this is going to give me the distribution that I want, right? And how can I write down this guy? Can you help me writing it down? So I'm going to use chain rule. What should be the first term? I write it down. You tell me if you agree or not. I write it down in this form. The probability of my action, given the state that I am in, times probability of the next state, given the action and state that I am in. Everybody's cool? This is just chain rule, right? So I started this chain rule by the red term, then times the probability of the yellow term given whatever had been used before, right? The green and red term, right? Everybody's clear? Questions? Okay, what is the first guy, this P? This is the policy, right? Pi. This is the probability of doing one action given that you are in one particular state, right? What about the second one? That is the transition given by your environment, described an MDP. MDP is going to tell you what is the probability of the next state given the current state and the action that you do, right? So you can replace these two by using your policy and your MDP, and that's it, right? You have it. Everybody's clear? Now, one thing that I'm going to do, I am going to put a pi here. You see here? And the reason that I put the pi here is because this expression, like the probability of the next state, given my current state, that depends on my policy, right? You see it here in this expression, correct? Right? So, and it makes sense. I mean, if I'm in this particular state, what is the probability of the next state? It depends on my policy. If I decide always go do that action, then I'm going to see always maybe one particular state, right? If I decide to just randomly do actions, I might see randomly different states, right? Everybody's clear? So that guy depends on the policy, and I can keep that pi here, but this is going to again disappear very soon, so no worries about that. Questions? No question? Everybody's clear? Great. So if you can have no question, now we now have both the transition distribution and also the other term that we had, so we can just replace it here. And what you're going to have is that your expectation of gt plus 1, given the current state that you're in, is written in this form, right? This is going to be the value function at the next state times the probability of going to the next state, right? Everybody's clear? And now I can, of course, replace it in this form. I mean, I have done nothing but just replacing this p pi in terms of the transition and the policy. And this is going to be a much longer version of the same equation. But we can actually write this down much easier. So, okay. Say I have one function. Say I have one function, function f, of s bar, and s bar is my next state, okay? And I want, so S bar is eventually st plus 1, right? The state that I'm going to be in time st plus 1. If I want to take the expectation of this guy, given that at time t, I'm in state S, how can I write this down? So this is a function, right? You want to take the expectation of a function with respect to its random variable. What do you do? You're going to write down the function f st plus 1. You're going to put st plus 1 to be one of the possible outcomes, say Sn, right? And then you multiply it with the distribution of that, the probability of that particular outcome, right? The probability that S, okay, maybe I take it a bit up. Sorry, that's here. Okay, that's good. The probability that st plus 1 equals to Sn, right? And then you're going to add it up over all possible cases. Everybody agrees? Everybody agrees on that? Okay. Now I want to take the expectation given that my state at time t is S. What should I do if I want to, what change should I do here? This is for the case when I don't have this guy, right? If I have this guy, what should I do? Add a condition here, right? So I'm going to add a condition here, right? Everybody agrees? This is the expected value of this function, right? Now if I replace this function here with my value function, v pi, what should I do? What should I change here? I replace f only with v pi, right? Do you see this expression in the slide? Yes? The second line, right? So you are computing the value at every single possible state, and then you multiply it with the probability of going to that state given that you are in your current state, right? And then you add this up, right? Everybody's clear? So that guy is eventually this one, right? The expectation of your value function at the next state, given that you are in the state S. Everybody agrees? Yes or no? Is it because of the lecture time, or is it some personal issue that you're not responding? Because in the morning, people are more responsive. So do you agree with me on that? Is it clear? Yeah? So this is eventually, if you expand this, you're going to have the second line, right? And you can compactly represent it in this form. So this means that the expected future return is eventually the expected value function when you think about the next state, right? When you are in this particular state, you don't know what is the next state, right? But since you have your MDP and your policy, you can find what is the chance of every single next state, right? So given that you know this distribution, that is P of the next state given my current state, you're going to say, okay, let's say that I went to the first state, right? What is the value there? So you put it in the value function. What if I go to the second state? Then the value is this guy, and so on till all possible states, right? And then you average it. This is going to be what you're looking for, right? Questions? Everybody's clear? No question? Okay, so if you got no question, then let me just replace it in the recursive form that we found. We started with writing this guy down, right? And then when we wrote it down, we had this term and the second term. And what should I put instead of the second term now? I should put this guy, right? Yes? So the expectation of the next future reward is going to be the expectation of the value function in the next state, right? And if you do that, then you're going to end up with this expression. So this one, right? And I can always expand it, right? I can write down that expectation of the next state in terms of the probability, right? Everybody's cool? So now, if you had what I was doing, that's okay. Take it from this point on, okay? Let's say that this equation is correct, okay? I try to show you that this equation is correct. But if you don't see it right now, you can take your time later to check how this is correct. Let's say that this equation is correct, okay? Now, this equation is what we call it the Bellman equation, okay? And you might say, the key point about the Bellman equation, I'm going to explain it shortly, okay? But how we ended up with this recursive equation, that you have the value function in one particular state S related to the value function at the different states. But if you don't see it immediately, that's okay. You can take more time at home to just recap this. But take this from my side. So the value function at any state is related to the other values in this form. Okay? This equation is correct. And this is what we call it the Bellman equation. Okay? Okay, so that is the Bellman equation. So the Bellman equation, what it's doing is just looking in one particular state, right? So you have multiple possible states, and then you're at one particular state. What does it say? It says that if you do know the value of all states, then the value of these states should somehow satisfy this equation, right? Let's say that somebody has already told you that for your particular policy that you are playing with, the value of every single state is something given, right? So somebody describes to you what is V pi S, okay, for every single state. Then if you want to make sure whether that is really a value function or not, then this equation should be satisfied, right? It means that you cannot simply throw a function and this is a value function, right? So your function must satisfy this equation. Everybody's clear? So this particular equation is going to describe a system of equations, indeed, that's going to help you to one particular policy without the need to go through all the expectation things that we had before. You might ask me how. Let's just break it down together. So let's say I am in one particular state, and say I have in total n different states, right? Now, what it says that the value of that particular state S that I am in is related to the value of all other n using this equation, right? Right? So I had the value of a state S1, value of the state S2, and so on till value of the state Sn, right? Now if I look at one state, then I can use value of the other states to just confirm this state, right? So in general, if I have value of my policy at state S1, S2 till Sn, then I can treat them as a bunch of unknowns, right? And then I can write them in this equation, right? Now, I'm going to have, definitely this green S is going to be one of those states, right? And for any state S that I put here, I'm going to have one equation, right? That equation, how many unknowns does it have? I'm going to solve an example, but try hard to see it right now. Then the example is going to make it more clear. Say that you don't know the value function, right? You don't know the value function. How many possible cases the value function could have? It could be V pi at a state S1, V pi at a state S2, until V pi is still state Sn, right? So your value function could have n different values at n different states, right? Now, if I just choose one of the states, then I can check the value of that state using this equation, right? Right? Now, if I write down that equation, how many unknowns are inside this equation? Yes?
Do we assume that we know R or not?
We know R. You can compute R. It's going to be?
Two variables.
Why two variables?
At any point
Yes, but just check it here. You are summing up over all possible states, right?
Right, at one of those ends.
No, it's not one of all those ends. You don't know which one it is. Just look at the equation only. So say I have 10 different states. Or not even 10, say I have 4 different states, right? If I have 4 different states, it means that I could have S1, S2, S3, S4, right? These are possible states. I'm not out of these states, right? I'm in one of them, right? Now, I choose this guy, and I want to write down the Bellman equation for that one. How can I write it? I'm going to say that V pi, this is the value of my policy at a state S1. It equals to, can you help me complete this equation based on that? It's going to be the immediate reward at S1 plus, what is else? Don't try hard to just fool me, because I'm not going to leave until you just explain this to me. So tell me what's going to be the next expression in this equation. What is it? Look at the summation. So there's going to be a gamma, and then I just open the bracket. What is the first term in that summation? Please? V pi at why 2? And it starts from 1. What is it? Times P pi of S1 given S1. What is the next term? Times S2. So this is going to go on, right? So let me finish this. So what is the next term? V pi is 3 times it's not enough only one of you, everybody. Last one. V pi times okay. So this is the first equation, right? Now, in this equation, let me see if we are lucky today. No. You don't have any color? Okay, it's fine. So now, this guy, this is the immediate reward. You can compute it. I'm going to do it. We did it last time. I'm going to do it again. So that one you know. It's not unknown to you, right? This guy, do you know it? V pi is 1. Do you know it? You don't know it, right? So this is unknown. What about this guy? Can you compute this? The probability of staying in your state S1, given that you are in state S1. Can you do it? Yes or no? Yes, because you know the MDP, right? This is gone, right? What about this guy? Do you know V pi S2? No? What about this guy? Do you know it? The probability that you go to state S2, given that you're in state S1, and you're playing with policy pi, you know the policy, you know the MDP, you know this guy, right? What about this guy, V pi S3? You don't know it. What about this guy? You know it. What about this guy? You don't know it. What about this guy? You know it. Now, how many unknowns do you have here in this equation? 4, right? Now, if you have a general case n, how many unknowns you would have? N. And this is one equation, right? How many of these equations you can write? N, right? In this example, 4, right? Because I can write this guy. Again, I can write the same thing for S2, S3, and S4, right? Everybody's clear? You got it now? Yes? So this Bellman equation, if you write it down for every single n, then you're going to have one equation. In every single of those equations, you have n unknowns, right? So you have n unknowns. You also have n equations, right? You have, these are your unknowns, right? And then you have n equations as well, and because of that, you have a system of equations which is theoretically complete, right? So you can solve those n equations for the n unknowns, and then you end up knowing the value of every single state. Everybody's clear now? So you see how this Bellman equation is going to make you get rid of all of those expectations? Yes? Questions? No question? Everybody's cool? Great. So if you got that, let's try this for this dummy grid world as we did before. I mean, we computed the immediate reward here last time. And I'm going to use that fact and write down the equations to see whether I'm going to end up with the values that we found out last time or not. Okay? Before I start, what is, don't look at this slide. What is the immediate reward when you are in a state 0? State 0 means top left. What is the immediate reward? 0, right? It's a terminal state. You go to the terminal state, you stay there, right? And no matter what you do, you're going to always have reward 0, right? So the immediate reward here is 0. This is why we have the first term, right? Now, look at this diagram here. This is showing you the policy. The policy is the direction that is shown in the diagram. Now, looking at this one, what is the immediate reward that you get when you play with this policy in state 1? And state 1 is the top right one. What is it? It's -1, right? Because when I am at this particular state 1, I'm going to move one step left, right? And each time that I move one step, I'm going to get reward -1. So the immediate reward given this policy is going to be -1, right? What about this other two states? What is the immediate reward in them? It's again -1. In any of these states, when I move based on this policy, I'm going to get to another cell, and because of that, I get the immediate reward -1, right? So that makes sense to you that immediate reward, the average given the policy is 0, -1, -1, -1, right? Clear? If I change my policy, this is going to change, right? For instance, if I make my policy at this particular top right cell to just move to right instead of left, what's going to be the average reward? Immediate one. Go ahead. -0.5, exactly. It's going to be -0.5 because it's going to hit the wall, right? So I change the policy, the immediate reward is going to change. Everybody's cool? So this is the immediate reward that I'm going to get in the particular state, each state, when I am playing with this policy pi. Now, the thing is that I want to use only this fact plus the fact that I don't know these values, and I've used the Bellman equation to find the values. Okay? Let's go ahead and write down the Bellman equation for every single state. So let me start with the state 0. So if I want to write it down for state 0, it's going to be the average reward in state 0 when I play with my policy plus the value of every other state. So state 0, 1, 2, 3, all the states in this setting, right? The value of all of them times the probability that I just transit from my current state 0 to that state. Everybody's clear? Now, when I am in state 0, what is the chance that I remain in state 0? 1, right? State 0 is the terminal state, right? When I am in that state, I'm going to remain in that state forever, right? So the probability is 1. What is the probability that I go to any other state? 0, right? So I'm not going to leave that state. So I can simply say that this guy, this is going to be 1 when the next state S bar is 0. It's going to be 0 anywhere else, right? So if S bar is 0, the probability is 1. I'm always remaining in my state 0. So I was in a state 0, and I'm going to remain in this state 0 with probability 1. And for any other future state, I have the probability 0, right? Everybody's cool? You see it? Right? Now, if I use this guy to just simplify this summation, what's going to remain in this summation? Go ahead and say it. Yeah, go ahead.
There's a 1 times 0 that gets left, which is 0 anyway, so it's all 0.
So it's going to be 1 times the value function at s bar equal by 0, and it's 0 for any other. So this summation going to get left with only one term, right? And that term is v of 0, right? v of pi at a state 0. Everybody seeing that? So this guy is going to be v pi at point 0. If you don't see it, I can write it down again. So look at this guy. We said this one is 1. This guy is 0, this guy is 0, this guy is 0, right? So these terms in the summation are going to disappear, only this one remains, right? And S1 for you is 0, right? So the outcome going to be 0, right? V of pi at 0. Everybody's clear? Okay, so this is going to be the equation. 1 point. I have just put gamma, the discount factor, to be 1 because I want to keep it simple. Okay? Everybody's cool? Okay. Now, looking at this equation, this is an obvious equation, right? V at state 0 equals by V at state 0. Obvious, right? It's not contradicting, but it's not giving any information, right? Everybody's cool? Now, let's go for the next state. The next thing that I'm going to do, I'm going to put my state to be 1, right? If I put my state to be 1, then I again write down the Bellman equation, right? Value at state 1 equals by immediate reward at state 1 plus this summation, right? Now, first of all, what is the immediate value, the average immediate value for this policy at state 1? -1. You are at this state. When you act with this policy, you're going to move left, so you're going to have immediate reward -1, right? So that first term is -1. We now need to compute this summation. What is the, say you are playing with this policy, what is the probability that you end up with a state 0 when you are at the state 1? What is it? 1. When you are at the state 1 and you play with this policy, you're definitely going to go to a state 0, right? Everybody's clear? What is the probability that you remain in state 1? 0. What is the probability that you go to 2? State 3. You are not going anywhere else. You're just going to the terminal state, right? So you can again say that the probability with this policy that you are seeing here, the probability that I transit to a new state, when this new state is 0, the probability is 1. When this new state is not 0, the probability is 0. Everybody sees that? Questions? No question? Now, if you got no question, what's going to be this term then? 0, right? So this whole summation again going to be v pi 0, right? Which means that the value of your policy at state 1, at this state, going to be the value of your policy at state 0 plus -1, right? Does it make sense to you if you just forget about Bellman? Yes, because with this deterministic policy, you definitely know what you're going to collect next, right? And when you play with this guy, you would say, okay, the value that I am here, right? The value that I'm going to collect at this state is going to be exactly the value that I collect in the next state plus the reward that I get in my move, right? I get -1, I go to state 0, and whatever I collect from then on, this is my value, right? Everybody's clear? Now, can you tell me what's going to be the next Bellman equation if you write it down for state 2? Just look at this, and intuitively, based on the diagram, tell me what's going to be the value of your state 2 given other states that you have in this diagram. So I want to write down the value v pi at state 2, and state 2 is the one on down left. Okay? What's going to be this guy? Can you tell me? minus 1, this is your immediate reward, plus. There could be a bunch of terms, but what should be here? It's going to be v pi at 0, because when you play with this policy, you're going to go in state 0, and this is the value. You just need to know that its value, right? So it's going to be value of pi at point 0. What about v pi at state 3? What is it? Go ahead, just say it. Minus 1 plus v pi at state 2. Because when you are at state 3, you play with this policy, then you're going to go to state 2. So whatever the value at that point is, plus that minus 1 that you're collecting in your move, is going to be your value, right? Everybody's clear? You see it now? Perfect. So you can put these two guys also here, right? These are your two other things, right? Two other equations. And now you have these three equations. The first equation, I just dropped it because it said v pi at point 0 equals by v pi at point 0, right? Which is obvious, doesn't give you any information, right? Now, you're left with these three equations. How many unknowns do we have? 4, right? Can I solve this? No, but do you know any extra information that's going to help you solve this? Terminal state. What is the value at the terminal state? It's always 0, right? So you do know that the terminal state has value 0, right? That is the state which gave you the non-informative equation, right? So you use the fact that state 0 is a terminal state, so the value is 0. Then you put value 0 there. It's going to give you the value of every single other state, right? v1 at state 1 is going to be minus 1. For state 2 is minus 1. For state 3 it is? It is? Minus 2, right? So this is going to be the value function. And this is the one which we computed naively last time without using Bellman equation.